And the second speaker today is Professor Patrick Tolksdorf. He is talk about the free boundary problem via the Prato-Grisvard theory. So please.
Thank you for the nice introduction. So yeah, I will talk also about free boundary problems. And I will actually present you almost the same theorem which Professor Shimizu presented to you. It's just slightly different in the range of P's we can treat, and yeah, we will use a completely different approach to tackle this free boundary problem. And this is a joint work with Raphaël Danchin, Matthias Sieber, and Piotr Mura. And also I would like to thank Yoshihiro Shibata for many discussions on free boundary problems, and also on the results yeah, on the Stokes operator with Neumann type boundary conditions. Okay, so let me start with motivation. And yeah, the motivation is the same as just Professor Shimizu had. So let's say we have a domain omega which is filled with some fluid, and this domain omega, it can move with time. So we have a free boundary, and so we have a domain omega of t which is filled by some fluid, and this fluid should be an incompressible viscous fluid.
Excuse me, you should change the screen, I think.
You see me? You see me and not what I'm writing?
No, sorry, Patrick, maybe
yeah,
you have to change your
screen sharing.
Go to the pages. Go to second page, I hope. No?
I think they just write here screen sharing was interrupted. I try again. So now you see everything?
Okay, now it's okay.
Okay. Thank you. Okay, so we have here on the right-hand side, we have our domain omega, our region omega, which is filled by some fluid, and it has a free surface. So the boundary of omega also depends on t, and it's filled by some incompressible viscous fluid. And we also assume that there's no surface tension, as for example, yesterday in the talk of Professor Shibata. And also no gravity. And yeah, you see, or we also assume that we want to treat, let's say, domains which are unbounded in all spatial directions, and yeah, also have a non-compact boundary. So it's the same example as in the talk of Professor Shimizu, where at initial time t, we simply have the half space. So omega of 0 is supposed to be the half space. So in this here is at time t greater than 0. Okay, so this is somehow the situation we would like to look at. And yeah, as you already saw in the talk of Professor Shimizu, we have a certain set of underlying equations. So we have the momentum equation. This is the same. Oh yeah, this is essentially the same set of equations also Professor Shimizu just wrote on the blackboard. So we have the momentum equation here, the first equation. There appears the Newtonian stress tensor, which is given by TVQ is just, 2 times the symmetric gradient. So we have here dv plus dv transposed minus q times the identity. We have the incompressibility condition, and on the boundary here we have the stress-free boundary condition. The n bar here will denote the outward uninormal to the boundary of omega of t. So n bar is the outward unit normal to the boundary of omega of t. And then we have here the fourth equation is just the equation which tells us, okay, that the normal fluid velocity at the boundary should be the same as the normal velocity of the boundary parameterization. So the boundary is parameterized by this function eta here. So eta parameterizes the boundary of omega of t. Okay, and then we have some inhomogeneous initial velocity, and we assume that the initial domain is just the upper half space. And as in the talk of Professor Shimizu, we are also interested in global and time solvability of this system. Okay, and there are many results, as you already saw in the talk of Professor Shimizu. So she gave a very good preparation for me. She did a very good review on the literature, and I think all of you know more about the literature than I do, so I will not talk about more names than she did. But we are somehow interested now in global and time solvability of this problem. And as you already saw, for example, also in her talk, is or also in the talk of Professor Shibata yesterday, is that one approach is to introduce a transformation of the domain into some time fixed domain. So we want to apply some transformation and only solve the equation then in some fixed domain. And so this is somehow what one is doing. And one very physically relevant transformation is this change into Lagrangian coordinates. So it was already explained by Professor Shimizu, but I will draw more pictures maybe. So we have maybe the Lagrangian picture. And we have some Eulerian picture. And in Eulerian coordinates, somehow we are like an observer from outside on our fluid domain, and we have our coordinate system, and we look at the particles, or we look at some particles, and there will be a new particle at every time at a fixed point x we consider there. So we have here some x coordinates. We have our fluid domain, which is filled by some fluid, and at some point x we will have a fluid particle which somehow started in the half space at a certain point, and this point will be called psi. So the Lagrangian variable will be called psi. We will have here in the Lagrangian picture just the half space, or let's say the initial domain, which in our case is the half space. And somehow the x variable, or if you want to transform from the psi variable to the x variable, you think about you start at the initial time at some point psi, and then you just let the evolution go. And at a certain time t, this particle, which was at initial time at xi, will be at the point x. And then there is a relation between xi and x, which was also written by Professor Shimizu in terms of an ordinary differential equation. So in the Lagrangian picture, we will also call the velocity variable u. So it will be the same notation as in the talk of Shimizu, but I'm sorry, the pressure will be called not Q, but capital P. Okay, and in the Eulerian picture, also as in the talk of Professor Shimizu, the velocity variable will be called V, and we call here the pressure variable capital Q. So, but I hope that that I will not confuse you. Okay. So as I said, if we want to write down the transformation, we look at some particle which is at some point x, and at this point x, this is, or let's say it's a particle which is at time t at this point x, and at this point, at this time t, there is a particle which started at initial time at some point psi. Okay, and if we want to get this, if we want to know where exactly this particle is at time t, then we start at psi, and we have to integrate along the velocity of the orbit of this particle. So we integrate from 0 to t, and then we have to integrate the velocity variable along the orbit of this particle. So we integrate along, let's say, the time s, and then along all previous positions of our particle, which started at psi. Okay, and this somehow gives us the coordinate transform, or if we, or let's say I just redefine something, namely this velocity of s comma x will then be called u. This is then the Lagrangian velocity, which we are looking at if we change the coordinates. Okay, so this will be defined somehow as the integral from u of s of psi ds. Okay, so we have here our Lagrangian velocity. And we have here our Eulerian velocity. Okay, and yeah, this is a coordinate transform. So we want this coordinate transform to be invertible. Yeah, for some fixed time t, we would like to have like an invertible transformation between the x variable and the psi variable. So, and if we would like to invert this, we would use the inverse function theorem. So we would take the derivative of the function x depending on psi, and we calculate this derivative. So here, if we take the Jacobian here of the psi variable, we simply get an identity. And here in the integral, we just pull the derivative inside the integral. So we have here a d psi u of s comma psi. Okay, so it's already in a quite good structure. So we have some identity plus some matrix, and to use the inverse function theorem, we would like that this Jacobi matrix to be invertible. And then we can simply use somehow a Neumann series argument in order to invert this Jacobian. So, but in order to use this Neumann series argument, you need that this integral here small. So you somehow need a control on this integral in order to assure that you have a global Lagrangian coordinate transform. So this term, and this shall be small in a pointwise sense. So this is supposed to be small in L infinity. Come on. So in L infinity, this is supposed to be small. So this is very important here. Okay, and if this is small somehow, then you can invert this Jacobian and you get, like, for example, this power series here. Okay. So if you, let's say, if you would have a control on everything, you could perform this Lagrangian coordinate transform, and then you obtain the transformed equations. So, and as in the talk maybe of Professor Shimizu, I will call now this here, this is the system LF, which you also saw in her talk. So I will call it also LF. And if you have these transformed, or yeah, then you simply want to solve these transformed equations somehow. And the good thing here is now that that this transformed equation is on a time fixed domain. So this is simply this is just formulated on Rn plus. Okay, but the equation looks much worse. I think already, like, yeah, yesterday in the talk of Professor Shibata, you already saw that this transformed equation is then yeah, quasi-linear equation and not a semi-linear equation anymore. Yeah, so, and due to this transformation somehow, the convection term, it vanishes into this material derivative. But at all derivatives which you take, so you get some dependence on the Lagrangian variable u. Yeah, this is appearing in the Lagrangian coordinate transform, and that's why I added here like small indices u. So we get all kind of derivatives and stress tensors, and also the normal vector. Everything depends now on u and is highly nonlinear. Okay, so and then we introduce the linearization. So we put the nonlinear parts on the right hand side. So I just put this here on the right hand side now, and this here as well. This gets this will get a minus sign. And I also put this here on the right hand side. This also gets a minus sign then, and then I introduce here the linear parts, so the divergence of the stress tensor of u comma pi p, and I have to take. I know I wanted to write it in red. Sorry. So you have here the divergence of the stress tensor of u comma p, and you also have to subtract it here on the right hand side. You introduce here simply again the divergence of u, then you have to add it also on the right hand side, and you introduce also here the stress-free boundary condition, or the stress tensor multiplied by the normal vector. The normal vector on the bound, yeah, of the upper half space is just minus the nth unit vector, and then you have to write it also here on the right hand side. Okay, so then, yeah, Professor Shimizu already wrote out like how these terms look like, and they get very, very big and ugly somehow. But it gives us a fixed point equation which we want to solve eventually. Okay, So how one estimates these nonlinear terms, or maybe some examples, I will present on Friday. And maybe at this point I can also like tell you some philosophical differences between the approach of Ogawa and Shimizu and our approach, namely, if I saw it correctly in the talk of Professor Shimizu, she reduces everything to, let's say, an inhomogeneous boundary value problem. And we do it differently. We first reduce the divergence equation to be zero. So we reduce the divergence to be zero. So we have to care about the equation divergence u equals to g. This will be the first step. This we will see on Friday. Then we will care about like the boundary equation with the side condition that the divergence of u should be zero. And then and today, or what is left somehow, is that we want to investigate simply the Cauchy problem with homogeneous divergence and homogeneous boundary conditions. And this, the investigation here of this system is somehow the most important part of our work. Yeah, and this is what I will start today to investigate. Okay, but as you already saw, or as already Professor Denk said yesterday, if you want to do an approach by maximal regularity, actually the most important question of everything is like, which function spaces do you use? So this is like the driving question. Yeah, and let's see, yeah, which function spaces maybe are maybe important to ensure that you have a global Lagrangian coordinate transform. This was our driving question. In the talk of Professor Shimizu, you just saw that she motivated the function spaces by a scaling argument, and then she considered scaling critical spaces. But we would like to ask a different question, like which is like the best function space to ensure you a global Lagrangian coordinate transform. So this is somehow our driving question. Because if we want to solve the original equation by changing the coordinates to a fixed time domain, we would have to ensure that at least the transformation makes sense for all times, right? So, and as I said to you, we needed that here, this term here, that this is somehow small in L infinity. To somehow invert everything. And then in the transformed equations, you saw that everywhere where a derivative stood, there will be some dependence on u. These will be highly nonlinear derivatives somehow, and everywhere will stand terms of this form. So, and you see here already you have to multiply with arbitrary high numbers or exponents of k, for example. So it would be good if, for example, if your function spaces, if they give you some control in L infinity of the gradient of u, and also if the gradient of u somehow lies in the Banach algebra to ensure that you can multiply arbitrary high that you can multiply the gradient with itself arbitrarily often. So these are like two side conditions one needs, for example, to ensure or to find good spaces, and one very good space which satisfies both of these properties is actually the space is a homogeneous Bezov space, namely this B dot n over P1. This is somehow like if you would use in let's say for inhomogeneous spaces, then somehow you have a threshold when you when by Sobolev's embedding theorem you only embed into LP space or LQ spaces or into Hölder continuous spaces, and it's not really possible to embed into L infinity, or you already embed into Hölder spaces, but then you give up already some information, right? But like the borderline space where you have this L infinity embedding is actually here this homogeneous Bezov space. So this space here, this will be like the important or like the borderline space which embeds into L infinity. So if we work in spaces where the gradient lies in B dot n over P1, then we can have, or then we would like to have control, or then we would get control on the L infinity norm. And the other good thing is that actually the space is a Banach algebra. So and this would ensure that that here we can multiply the gradient of U arbitrarily often by itself. Okay. So and if you're in homogeneous Bezov spaces, you can somehow switch around the scales and the gradients. So you somehow have that the gradient or the derivative of U lies in B dot n over Pp1 if and only if twice its derivative lies in B dot n over P minus 1 P1. So and as the Stokes operator is a second order operator, this year will be a candidate as a ground space for our maximal regularity. Okay. So, but then the question is, okay, now we identified somehow a ground space which is somehow nice in the spatial sense, but we don't only need some bounds here, for example, in L infinity. Also, we need to control the L1 in time norm, right? So the driving question is actually now whether it is possible to prove maximal L1 regularity with this as a ground space here. So is it possible to prove maximal L1 regularity with ground space X is given as B dot n over P minus 1 P1. Okay, so this is somehow the driving question. And this will be like the main part of the talk today, or the second part, let's say. But before like I go into this abstract theory about this, so this will be like some abstract theory which comes from the classical Prato-Grisvard theorem from 1975. And before I do this, I will just briefly state our main result on the solvability of the equation LF, so the transformed equation into Lagrangian coordinates, and then you somehow have the possibility to compare it with the theorem of Ogawa and Shimizu. So this is by Danchin, Iber, Mura, and myself. And yeah, up to now, actually, we only considered the case n equal to 3. So we are only in 3 space dimensions. And let's say, and we take a number p between 2 and 3. So it's between, like, if you think in n dimensions, it's between n minus 1 and n. And this is already the main difference between our theorem and the theorem of Ogawa and Shimizu, namely they treat p's which are larger than the space dimensions, and we treat p's which are smaller than the space dimensions. So and then actually the whole theorem is the same. So then there exists a constant c greater than 0, such that for all initial velocities v naught in b dot 3 over p minus 1 p1 of the half space, the spaces are also defined in the same way as Professor Shimizu just showed it, with the side condition that the divergence of v naught is 0. Okay, and v naught should be small in this norm. So v naught is supposed to be small in b dot 3 over p minus 1 p1. And for all such v naught, there exists a unique solution UP to the system AF, such that also here we have some L infinity bounds. So U is bounded continuous in R plus with values in B dot 3 over P minus 1 P1. N is 3. So and also the time derivative of U, the second derivatives of U, and the gradient of the pressure, they lie in L1 in time, globally in time, with values in B dot 3 over P minus 1 P1. Okay, so this is somehow our main result. And as I said, the main difference here is actually, is here the condition on P. And the other maybe more important difference is that we have completely different approaches to this theorem. Okay. So, but let me start now to talk about how. So, as I said, the most important part for us was to have maximal regularity for the Stokes system with homogeneous divergence and homogeneous boundary conditions, and we only have an inhomogeneous forcing and an inhomogeneous initial condition. And this is then the classical, like, maximal regularity question for operators or for abstract operators A. And in order to derive estimates for such an operator, we will now consider more closely the theorem of Prato and Grisvard. Okay, so the framework of the theorem of Prato and Grisvard is the following. You have a Banach space X, and minus A is the generator of a bounded analytic semigroup, and that's it. And this will already be the assumptions for the theorem. So there will be no UMD spaces, no R boundedness. These are just the assumptions of the theorem. So this is a generator of a bounded analytic semigroup. Okay. And then, as Professor Denk yesterday pointed out very clearly, we have a certain maximal regularity question. Namely, let's say we have some integrability Q between 1 and infinity, and we can pose the question first also for Q equal to 1 or Q equal to infinity. And we take some time between 0 and infinity, and we could include t equal to infinity. And then the question is, okay, does for all functions f in AQ, so I take a right-hand side f, which is AQ integrable here, and I take some initial conditions x, which should be in some appropriate initial data space. Yeah, yesterday in the talk of Professor Denk, this was simply the trace space. This was a trace space, which was also, I think, denoted by x gamma. So this is, let's say, this should be some appropriate space. And actually, Professor Denk, he already pointed out that it suffices to consider only x x equal to 0. But does for all functions f and aq and some initial conditions in some appropriate initial data space, does then each of the both summons on the left hand side also lie in LQ? Yeah, you know that if the right hand side is in LQ, then the left hand side must be in LQ. But as the left hand side consists of two summons, they could somehow cancel out the bad terms. And then the question of maximal regularity is actually whether each of the both terms here lies in AQ. Okay. So this is the maximal regularity question. And the unique mild solution here to this abstract Cauchy problem is actually, it's given by the variation of constants formula. So you have u. You have that u of t is given by e to the minus ta x plus plus the integral from 0 to t over the semigroup e to the minus t minus sa f of s ds. Okay. And I will now concentrate more on the blue term, and in the end, I will also care about the semigroup term. But first, I will just consider the blue term now. Okay, and if you want to answer this maximal regularity question, you saw that this question requires complicated theory to answer this question satisfactorily. And there, yeah, you could see already the details in the talk of in the talks yesterday of Professor Denk and Shibata. And the problem somehow is, the problem somehow is that if you want to do everything you saw already yesterday, you could reformulate this blue term into some Fourier multiplier operator. And then it's a question whether lambda times the resolvent is a Fourier multiplier, and these Fourier multiplier theorems they are only valid like if you add some geometrical structures to the underlying Banach spaces, like this HT or UMD property, and you need some stronger notions than simply boundedness in Michelin's theorem, and this is then the notion of R-boundedness. So there's some big machinery, and it took a very long time, or in the development of maximal regularity, it took like some decades in order to work out this whole theory. But actually this theory, or one of the first abstract results on maximal regularity, is the theorem of Prato and Grisvard. And they also considered this maximal regularity question. And the idea of Prato and Grisvard was that the answer to this question, it's always yes. If you have in any Banach space, and if you have like a generator of a bounded analytic semigroup, the answer is always yes, but you have to change the space. So somehow this complicated theory here about R-boundedness and everything, it arises from the fact that you want to choose a space X, and on this space you want to have maximal regularity. But let's say you start with some space X, and you want to ask whether this operator satisfies some maximal regularity, but maybe on a different space. So you can change the space. And then Prato and Grisvard said, yes, then it's possible to prove maximal regularity. Okay. So in this sense, the answer to this maximal regularity question is always yes, somehow, if you are really willing to change the space. And let's see how they change the spaces. So we have here like a definition. I have to fill something here. So we take some q between 1 and infinity and some theta between 0 and 1. And then we define a space dA theta q, which is defined as all elements x in X, such that t to the 1 minus theta A applied to the semigroup applied to X lies in the space LQ from 0 to infinity with respect to the measure with values in X. So it's like a Buchner space, and we have the measure, we have the H measure, the T over T. Okay, so this will be actually the space in which we will prove maximal regularity, and we will endow this with a norm X. So the dA theta q norm of X is defined as the Banach space norm of X plus this term here, somehow the norm of this term. So we have here the norm, the LQ norm with respect to the H measure of t to the 1 minus theta A e to the minus TA X in LQ 0 infinity with values in X and with respect to the H measure. Okay, so this is the space which Prato and Grisvard considered, and then they proved the following theorem. Okay, so they proved in 1975, so it's already quite a while ago, that if either you have a finite time interval or the operator A is invertible. So you need either t less than infinity or 0 in the resolvent set of A. Then for all numbers between 1 and for all numbers q between 1 and infinity, 1 and infinity are included, and for all theta between 0 and 1, that for all right-hand sides, which are now in AQ with values in this dA theta q space. So this is somehow like a nicer space than the ground space X. So you take some nicer f, you define the function u here from the variation of constants formula. This was the blue term. And then the assertion is that the time derivative of u and au satisfy a maximum regularity estimate, also with respect to the LQ norm with values in this dA theta q space. So you have a classical maximum regularity estimate, but in another space. That's the important message here. And one other important thing here in this theorem is that here the second index q is the same as the integrability index q. Okay. And actually this theorem is so important because because actually one can characterize, I will talk more about this on Friday, but one can characterize the space dA theta q as a real interpolation space between x and the domain of A. And this is somehow a Bezoff space. So if you are already interested, if you are only interested in maximum regularity in Bezoff spaces, then it's good that you can change the norm somehow. It's not a bad thing, it's a good thing actually. And so what we proved in our paper is a homogeneous version of this Prato-Grisvard theorem. Namely, the point here is that this condition here, we want to have infinite time. So we would like to have t equal to infinity, and but we have an operator. It's a Stokes operator on the half space. It's not invertible there. Yeah. So we don't have this condition above. But somehow the hope is that if you somehow have a homogeneous version somehow of this theorem, that you can skip this assumption above there. Okay, and so this is the following is our homogeneous version of the theorem. So I simply deleted the first line, and what is what you barely see here, I added a dot here over the A. So I changed again the norm. So we have the same maximum regularity statement, but again I changed the norm, and we simply took the homogeneous version of this norm. So dA dot of theta q should simply be the LQ norm of the semigroup term. So we deleted the ground space information, so that we also have to control x in the ground space. We only want to control t to the 1 minus theta a applied to the semigroup applied to x in LQ with respect to the Haar measure. And then we have the same theorem, like a homogeneous version of this Prato-Grisvard theorem. And we can skip the assumption that either the time has to be finite or a zero has to be in the resolvent set. Okay. And now in the remaining part, I would like to prove this theorem for you. It's really not a hard theorem. It's actually quite it's a proof which you already could do in a class on integration theory, when you would know something about semigroup theory in advance. So, but I will, because we are interested in the case q equal to 1 and t equal to infinity, I will prove this here for q equal to 1 and t equal to infinity. Okay, so we take a function f in L1 with values in dA theta 1, and here I take the inhomogeneous space because there are some. I see also there's a question.
Excuse me, there is a question from Professor Terasawa.
I have a question.
Mm-hmm.
So d dot a theta q homogeneous space is not included in X. I don't see the inclusion.
So this is some subtle question. One can prove two versions of the theorem. You can, and this is what I do now. I assume that I have a function f, which is in the homogeneous space, and then I only prove inhomogeneous estimates. So there everything is okay. It's included in X, and I only prove a homogeneous estimate. But and then I would, so in the end I would have to do a density argument to get all to get all homogeneous elements somehow. Or one can also like do it differently. Actually, we did it differently in our work, where we directly defined an inhomogeneous space D dot A theta Q. So we introduced some frameworks which resemble to other homogeneous spaces, and then we already defined the space, and we didn't need this density argument somehow.
I just want to know, maybe if there is some thing like distribution space, it's easy to treat homogeneous space in this case also, I think.
Yeah, we defined something like this, like because one already knows like that the space should be somehow included in the sum space between X and the domain of A, or the domain of some homogeneous A somehow. So we defined somehow, we assumed that there was like a larger space, something like a distribution space, which contains somehow this ground space and this domain of the operator.
Okay, thank
you.
Homogeneous.
Okay, you're welcome. So, but now I thought this might be too complicated for the talk here. So I will just prove homogeneous estimates for some inhomogeneous functions. So we take f and L1 with values in dA theta 1. And then we simply start. So we write down what we want to estimate. So we want to estimate A. So if we can estimate this term here, A applied to U, then we also can estimate the time derivative of U, since it solves the equation. So we write down simply this term here in the norm. Theta 1. And I put the dot here. Okay, so let me write down everything. We have here, we have outside, we have the L1 time integral. So there's here integral from 0 to infinity. Then we have an L1 integral from the Prato-Grisvard semi-norm. So also an integral from 0 to infinity. We have here like some tau to the 1 minus theta. Then A applied to the semigroup. And here is already another A. So we have an A squared applied to the semigroup, e to the minus tau A. And we apply it to the Cauchy integral. So the integral from 0 to t over e to the minus t minus s a f of s ds. Okay, and then we have here d tau over tau and dt. And let me already do something here in this equation. Let me perform like a small substitution. So we substitute t minus s by some s tilde, let's say. So we can rewrite this integral here as follows. So we have here e to the minus sa f of t minus s ds. So we can rewrite it already in this way. And I see I forgot the norm bars. So here the norm in the X space. Okay. And because here this second index is 1, we have here also a 1. Okay. So then we pull in everything. So we take the semigroup term here, pull it into the integral. Then there's by the semigroup law an e to the minus tau plus s applied times a. And as it generates an analytic semigroup, you can estimate t times a times the semigroup uniformly in time, right? So you somehow use the analyticity of the semigroup. You get here, so with the outer integral, nothing happens. You have then the second integral from 0 to infinity, the integral from 0 to t. Then you have here the tau to the 1 minus theta. And then you apply this analyticity and you get some s plus tau here. And then there's only an a applied to e to the minus, let's say, 1/2 times s plus tau applied to a, then applied to f of t minus s x ds d tau over tau dt. And we put here a constant because we use the analyticity. Okay, and then what do we have to do next? Now we only use Fubini's theorem and substitutions several times, and then we are done actually. So let me see. We now put the dt integral by Fubini. We put the dt integral into the innermost integral now. So let me copy everything. So nothing will happen now. Almost nothing will happen. So okay, so I just copied the term. ID. So now we use something differently. We use Fubini. Okay, and we put the dt integral. We put the dt integral at the innermost part. So we put it here. Okay, so this was Fubini, and we have to change something. Namely, we have to integrate the innermost integral now from s to infinity. So this is from s to infinity. Okay, and then we in this one step we can even do more. Now we use if the t integral is at the middle, we use substitution rule. So we take t tilde as t minus s. Okay, and then we can simply, so then we integrate actually from 0 to infinity, and we integrate here over t tilde. Okay, so this was this step. Now you see, now we would like to put the which integral now? Now we would like to put the d tau integral in the middle and perform another substitution. Okay, so I put the d tau integral in the middle. Let me again copy everything. Yeah. It always takes a time. Okay, here it is. So now we simply put the tau integral in the middle. So we use again Fubini. And we use a substitution that, let's say, tau tilde should be s plus tau. Okay, so we get here somehow. So we get here a tau tilde. We integrate from s to infinity. we get here a Tor tilde, and the Tor will be a Tor tilde minus s. So we have here like a Tor tilde minus s to the 1 minus q theta, and here's a tilde, and here is also a Tor tilde minus s. Okay, and now you see already, now we almost won somehow. I might, because my time is over now, I will skip one step. So you see here, here we only have the Tor, here only we have the t. Now we can put the ds integral in the middle, and we can evaluate the integration here over these terms with the ds integral. And so this is just again Fubini once, and then integrate, and then simply evaluating the integral, and the outcome will be the following, namely constant times the integral from 0 to infinity, integral from 0 to infinity over Tor to the 1 minus theta, and then we have A applied to the semigroup Tor A f of t x d Tor over Tor and dt. Okay, and this is already the semi-norm we had. So this is already f in L1 from 0 to infinity with values in dA dot theta 1. Okay, and this is the proof. So you saw we only used the analyticity once, and then only Fubini and substitution rule, and we got the maximum regularity result with respect to these spaces. So okay, so I think my time is up now. I will continue next time by applying this theory then, or by saying how to apply this theory to the Stokes system.
Okay.
Thank you for your attention.
Thank you very much. It's very nice talks. Okay, so do you have any question, comment?
I have a question.
Okay, please.
Could you show the Grisvard Prato theorem again?
Mm-hmm.
Could you show the Prato-Grisvard theorem?
Yes, so this is like the original formulation.
So I think so dA theta q is something like Bezos space, right?
Yes.
And
Yeah.
and I wonder, so LQ, how much can one generalize space LQ? One can change into Sobolev space or trivial Wilson space or Bezos space. What can be done for a generalization for LQ?
So for the time variable.
Yeah.
I don't know.
Okay.
They didn't think about it.
Okay, that's okay. Yeah, thank you.
All right, maybe I want to get one more or two more questions or comments. I really worry about the time for you. Can you? I mean, the day after tomorrow you will give one more talks, but
Yeah.
Then can you?
I will not be able to prove everything, but I thought
No,
maybe
it's not necessary. But
the proof is so easy, so I thought you have to see it to believe it.
Today you prove in some sense the Prato-Grisvard on a homogeneous case. Therefore, you can.
Yeah, like the homogeneous
you don't need
estimate,
the assumption of D0 is in resolvent of A. So
yeah.
T equal infinity. I catch you this one. And then maybe you will talk about how to apply this problem to the concrete Stokes problem for the.
Yes.
Okay, and then how about the nonlinear problems? That may be different story, but okay.
Yeah, I mean, you have to like you have to care about the boundary value problems somehow, but they are not so complicated as so somehow the point is that that here the complicated things are like in the application of the Prato-Grisvard theorem, and then we have like an easier approach to the inhomogeneous boundary problem, for example, because we don't have the side condition that we need to fulfill the whole Stokes system, but only the divergence condition. So this will be easier. In comparison to Ogawa Shimizu, they will care about this boundary, so they will really analyze in a systematic way this boundary value problem, and they will somehow get rid of the F and the initial condition in an easier way, because they can simply subtract, I don't know, whole space solutions or something like this. So somehow this is like the different philosophy of where you put the difficulty.
Okay, I see. Okay, very good. Okay, now maybe it's better to stop it. Thank you, because the time is almost resuming. Okay, so thank you, Professor Tolksdorf. Sorry. So maybe I'm looking forward to hearing you again the day after tomorrow. Okay, thank you.
Thank you.